Hello everyone, welcome to my presentation. I'm Huidi Wang and I'm from China Jiliang University. My topic is Implicit Randomized Progressive-Iterative Approximation for Curve and Surface Reconstruction. My presentation is divided into 5 parts. Introduction of the implicit curve and surface reconstruction, the IRPRA method for curve and surface reconstruction, the convergence of the IRPRA method, numerical results and conclusions. For the given unordered point set Pi, I from 1 to n, and the associated oriented unit normals Ni, I from 1 to n, the implicit B-spline curve fitting the unordered point set is the zero-level set of fxy. fxy equals sigma I from 1 to n mu, sigma j from 1 to n nu, Cij Bij xy, where Bij xy equals Bix Bjy I from 1 to n mu, j from 1 to n nu are the products of two B-spline bases with the uniform knot vectors. Xy is determined in ohm, and Cij I from 1 to n mu, j from 1 to n nu are the control coefficients. These control coefficients are determined by the minimization of the sum of the squared algebraic distance. And the implicit surface reconstruction can also be summarized to minimization of the sum of the squared algebraic distance. For the implicit curve and surface reconstruction, many implicit algorithms are proposed. For example, the Blowy model, the algorithm based on the sun distance function, the MLS method, the MPU method, and the method based on sets of non-conforming linear functions with spherical supports, the VIPSS method. However, the actual spurious sheets may be generated outside the objects. To avoid these accuracies, many methods are proposed. For example, a distance fit is introduced to construct an approximation with a regular grid. The Poisson and Grand Poisson approaches are introduced approximating the indicator function respectively. The regularization terms such as the total variation terms, the global tension terms, the ridge regression terms are introduced. The implicit the IPRA method are proposed. The IPRA method is an extension of the progressive-iterative approximation method for the implicit curve and surface reconstruction without any explicit minimization computation. The PIA method is an efficient approach for data fitting. By adjusting the control points iteratively, the PIA method generates a sequence of curves and surfaces whose limited curve and surface interpolates the points. For the IPRA method, the iterative process is deterministic, and the control coefficients of the implicit function is updated by applying all of the elements of the collocation matrix at the same time for every iteration. This may affect the efficiency and the computation cost of the curve and surface reconstruction. Motivated this observation, we propose the implicit randomized progressive iterative approximation. Next, we introduce the IRPRA method for curve and surface reconstruction. For the given unordered point set Pi from 1 to n and the associated unit normals Ni from 1 to n, we add the actual offset points Pi from n plus 1 to 3n with sigma. Sigma is a small distance. We give the condition of the satisfying condition of the generated offset points, we denote B and the vectors gamma I from 1 to 3n and omega. Then, based on the above preparation, we construct the initial implicit B-spline function with Cij0 equals 0, I from 1 to n mu, j from 1 to n nu. By compute the difference vectors for the data points, we determine the index site I0 and the probability related to the index site. The difference vectors for the control coefficients is computed, and the new control coefficients of the implicit B-spline curve is computed. Then we construct the new implicit B-spline function f first xy. Similarly, at the rth iteration, we have the difference vectors for the data points by determining the index site and running through the index I alpha belongs to I alpha with the probability. We compute the difference vectors dirt ij alpha. The alpha plus 1 difference vectors for the control coefficients are computed, and the alpha plus 1 implicit B-spline function is constructed. The implicit curve is the zero level set of the implicit B-spline function, and it is and the implicit B-spline function is constructed similarly for the surface reconstruction. Next, we present the convergence theory of the IRPIA method by the lemma. The convergence theorem let the linear system Bx equals B be consistent if the initial vector of the control coefficients C0 is equal to 0. The IRPIA method for the implicit curve reconstruction converges to the least null result. Next, we show the numerical results of the IRPIA method. It shows curves reconstructed with the point cloud sampled from the Cohen's curve and flower model. The blue points are the initial points, and the red lines are the reconstructed curves of the 5th, 10th, and final iteration steps. It shows curves reconstructed with the point clouds sampled from the butterfly and dolphin models. It shows the surfaces reconstructed from the clouds, point clouds sampled from the double torus model. And it shows surfaces reconstructed from the point clouds sampled from the torus model and the Max Planck model. It shows the surfaces reconstructed from the point clouds sampled from the Abedolo model. And it shows the surfaces reconstructed from the point clouds sampled from the fertility model and the fertility and the Biot model. Table 1 Table 1 shows comparison of the IPIA method and the IRPIA method for the curve reconstruction. Table 2 shows the comparison of the IPIA and the IRPIA methods for the surface reconstruction. From the tables 1 to 2, we can see the MR and CPU of the IRPIA method is better than the ones of the IPIA method. The implicit randomized progressive-iterative approximation method is developed for curve and surface reconstruction by adjusting the control coefficients with the probability. The method reconstructs the sequence of curves and surfaces which converge to the least node solution from the point of view of the mean square error. Compared with the IPRA method, the IRPRA method can be more efficient with the faster convergence rate and the least computation complexity. That's all. Thanks.